In 1885, Balmer first proposed an empirical formula to describe the hydrogen absorption spectra, which is discrete. It is a milestone in the history of optical spectroscopy, because in his days, there was no atomical theory whatsoever apart from the simple hypothesis by John Dalton that atoms are tiny, tiny particles with mass, without electrical charge, and that's it. That's it. So the Balmer's first mathematical formula to describe the experimental observation is very important. However, when we look back, it would appear that Balmer's formula is not that so difficult to obtain. Let me show you how to rediscover Balmer's equations. This is absorption spectra of hydrogen gas or hydrogen atoms. From here, you can see that the dark line here represent the absorptions by hydrogen. And the horizontal axis is wavelength. The first impression is that the interval between adjacent dark line decrease increasingly toward a limit or a minimum wavelength. So how can we describe this pattern by using the basic algebra? Okay. Well, first of all, we will use the integers, right? Because these patterns are discrete. So we are going to use integers as a variable. To start with, we can assume that the minimum wavelength, can we simply denote the minimum wavelength here is just 1 as a unit. We use that minimum wavelength as a unit. Therefore, the wavelength of this limit would be simply 1. Other wavelengths would be a multiple of a constant relative to this limit. Therefore, we can write the lambda for other positions as the form as 1 divided by something smaller than 1. If we just simply use an integer here, we can reduce the value. However, the sign is not right, because if n is larger than 1, the lambda became a negative number, which is physically meaningless. So the second trial we can use is just let lambda equal to 1 over 1 minus 1 over n. Perhaps this is one of the first trials Balmer used in his work. In this case, n can be an integer larger than 1, say 2, 3, 4, and so on. In addition, we can also introduce other trial formulas. For example, we can perhaps put an integer. We can use n squared instead of n squared. And in addition, we can consider another possible form as 1 divided 1 minus a constant. A, can we call this A over n squared. So these are 4 trial and error method you can use if you want to describe, if you want to find empirical formula based on the experimental observation. Okay. Before we go further, can we just write the Balmer's original formula published in 1885? Here we are. This is Balmer's original formula. He used a constant. Here I just simplify that constant as 1. Okay. Is equal to, this is his formula, m squared divided by m squared take away of n squared. Okay. The n here is a constant 2, m is integer from 3, 4, 5, and so on until infinity, because that will reach to the limit of this minimum wavelength. With the rest after that, what you can do is just use a piece of paper and pen to just use the different trial formulas to see which formula can be used to describe the experimental result. Now, because we have online plot here, let's just show you how to use Desmos to finish this work. Let's go to the Desmos. Okay. Now, we have draw the curve here, which is used Balmer's formula. So presumably this is also consistent with the original experimental data. So this is a curve we want to model, okay, use a proper mathematical formula. In the first place, we can use this formula as I show you that L is a wavelength equal to 1 divide 1 take away A divided by X. Here we use X as continuous variable, and A is integer 1 here. Okay. Now let's change A, is handy. Okay. A is changed from the 1 to 3. Let's just slow down here. You can see in the first formula, it would appear impossible to find the best fit, no matter what. So if the K, when A equal to 1, 2, 3 in this region. Next, we can try another formula. Okay. We simply use square to modify the first trial. Then let's vary the A. Before that, can we switch off the first model? Aha. It would appear that this is actually a correct formula compared with experimental result. So if you just adjust this A into the integer, 9, 2, here, you will see that this fit is perfect. So in older days, it would take a longer time without use Desmos. But this demonstration shows that it's not that challenging to find the Balmer's formula if given that if we can just follow these instructions. I hope this short demonstration will encourage you to do more research in science, and including rediscover some of the important works by other physicists in the past.